Alright, so decomposition is going to be our second type of chemical reaction. Decomposition is exactly what it sounds like. I'm breaking down into my pieces. I'm decomposing. The general form is going to be AB, so a compound breaking down into A plus B. It's two pieces. And the kind of classic identification of a decomposition reaction is that it only has one reactant. So whereas synthesis only has one product, decomposition is the exact opposite. So there are four types of decomposition. We're going to talk about each of them kind of one by one. The first is a binary compound. So a binary compound is a metal and a nonmetal, and it's going to break down into its elements. So it's going to break down into that metal plus the nonmetal. Metal carbonates. Carbonate, remember, is a polyatomic ion. So my purple and pink sheet's going to become very important again in identifying those polyatomic ions. Metal carbonates decompose into metal oxides and carbon dioxide gas. Third, metal hydroxides. Metal hydroxides are the exact opposite of what we saw forming in synthesis reactions. So when a metal hydroxide breaks down, it's going to break down into metal oxide and water. And lastly, metal chlorates. Metal chlorates, again, chlorate, being a polyatomic ion, is going to break down into metal chlorides and oxygen gas. So one of the benefits of the reference tables is that all of this is outlined on page 6 of your reference table. So if you grab your purple pink sheet and turn to page 6, you will find that all the rules for decomposition, synthesis, single, and double replacement are listed for you. So when you're taking your quizzes and tests, I should expect to see you flipping through that packet, finding those rules and using them in predicting your products. So let's do some examples. First we have sodium carbonate, and I know that's carbonate because of the CO3 that's present, and that's a polyatomic ion. So if I look at my reference table on page 6 and follow the rules for decomposition, metallic carbonates are going to break down into metal oxides and carbon dioxide gas. So the big piece here is to identify what the metal is. Remember that metals are cations. They're always going to be written first in the formula. So the metal is going to be sodium, and sodium is going to bond with oxygen. Based on my periodic table, I know that sodium has a charge of +1, whereas oxygen has a charge of -2. When those crisscross, I'm going to form sodium oxide plus CO2 gas. Remember that CO2 gas is never going to change. So now I can count to determine whether or not I'm balanced. I have 2 sodiums on my reactant side, 2 sodiums on my product side. 1 carbon on my reactant side, 1 carbon on my product side. 3 oxygens on my reactant side, 3 oxygens, 1, 2. 1 plus 2 is 3 on my reactant side. So that is now balanced. Next up is potassium chlorate. I know that's chlorate because ClO3, -1, is a polyatomic ion. If I'm unsure of that, I should definitely double check my reference table to ensure that that is present as a polyatomic. So metallic chlorates are going to break down into metal chlorides plus oxygen gas. So again, I need to identify my metal. It's going to be what's written first in my reaction. That's going to be potassium. So potassium, which has a +1 charge, and chlorine, which has a -1 charge, are going to form KCl. The next product in every metallic chlorate is going to be oxygen gas. Now, oxygen gas is written as O2 because oxygen is a diatomic molecule. It only exists bonded together. Therefore, I have to put that 2. It has nothing to do with the charge of oxygen. Now I'm going to balance. I need to count. I have 1 potassium on each side. I have 1 chlorine on each side. But I have 3 oxygens on my reactant side and only 2 oxygens on my product side. So I'm going to start by balancing those. If I put a 2 in front of potassium chlorate, I now have 6 oxygens, which I can balance by putting a 3 in front of O2. Now my potassium and chloride are unbalanced. So if I put a 2 in front of potassium chloride, KCl, now I am balanced. I have 2 potassiums on each side, 2 chlorines, and 6 oxygens. H2O, water. Water is considered a binary compound. We do water very differently, so sometimes we count it as HOH, sometimes we count it as H2O. For the purposes of decomposition, we're going to leave it as H2O. we're able to easily identify its pieces when we keep it as H2O, and those are going to be two elements, H and O. Now I wrote H2O2, and that is because these are diatomic molecules. H2 and O2 only exist bonded to another atom of themselves. Now I need to balance. I have two H's on each side, one O on my reactant side, two O's on my product side. So I'm going to start by balancing my O's. Now my O's are balanced. I have two O's on my reactant side, two O's on my product side. But my H's are imbalanced. I can remedy that by putting a 2 in front of H2. Now I am balanced. Alright, MgCl2. MgCl2 is going to be a binary compound. It has two elements, Mg and Cl. So when it breaks down, it's going to break down into its two pieces. Magnesium, which is a metal, and chlorine. Now, don't let this fool you. I have a 2 here and a 2 here. This is because it's diatomic. This is the charge on magnesium. Those 2's both are required, but they're there for different reasons. So you have to be very careful and be able to keep that straight in your brain. So now I can balance. I have one magnesium on my reactant side, one magnesium on my product side. I have two chlorines on my reactant side. I'm going to erase this little circle, so that it becomes a little easier for you to see that too. And two chlorines on my product side. So at this point I am balanced. I don't have to put any coefficients. My equation is already balanced. Alright, and last for decomposition we have calcium hydroxide. The 2 here is due to the charge of calcium, which we know has a 2+. So if I look at page 6 of my reference sheet, I can see that metallic hydroxides break down into metal oxides and water. So Ca with a 2+ charge and O with a -2 charge. When I crisscross those, I'm going to end up with just CaO, because we don't need to write charges, and 2 and 2 reduced to 1 and 1. And the second product is going to be water, H2O. So now I can balance 1 Ca on my reactant side, 1 Ca on my product side, 2 oxygens on my reactant side, 2 oxygens on my product side, 2 H's on my reactant side, 2 H's on my product side. So that's decomposition in a nutshell. Next we will talk about single and double replacement.